Um, it's my unexpected pleasure to introduce Mariano Sigman to this session. He did some of his PhD and postdoc work in New York, and then later on with Stand Their Hand, which we saw in a talk last week here. But above that, I can say that Mariano is probably one of the funniest and most engaging speakers I've ever seen giving talks. So I really, when I came through the door, I didn't even know what the title of the talk was, but I knew that Mariano was giving it. So I know I would enjoy it. And now I find out that the title of the talk is The Construction of Confidence, which is, of course, about social psychology, which is one of his main contributions to the field. So I'll let him do his show.
Thank you, Salva. It's actually, I think, a very friendly and nice introduction, but it turns out to be very bad because this is going to be a very boring talk, I think. Or at least I thought I should bring a more technical course for the technical talk here for the course. It's also maybe like a 3-hour talk, which I know it's very bad news, but obviously I'm not going to speak for 3 hours. I don't plan to go to the very end of it, so it will be much better. And I just learned that that's your very last talk, so you must be all exhausted and tired. We're just having a discussion on whether saturation or giving some time is the best way for the brain or for you to learn. I'll go a bit for the second one, although I'm told that I should go for the first. And so I think that what I want to say is that I don't have any intention to make it to the very end of my talk. There's no way I'll make it. And if you do stop me for questions, it's going to be much better and maybe even fun or entertaining or something. So it talks about confidence. I've been working in confidence for the last maybe eight years or something. It's a topic, I'll tell more about that, but it's a very old topic in psychology and philosophy, of course. But only very recently it's gained like a lot of attention in neuroscience. So in like what I'd say more like computational or systems neuroscience. And I'd like to make a little bit the bridge between these things. So I'm going to start. Of course, we all know what confidence is. I'm not going to define it. I'm just going to give you a small game or experiment we play in the game. This is a fixation point, and those are letters. And you should look at them. I'm going to ask you something about these letters. So take a look at them. You can look at them for 5 seconds or something, whatever time you want. We give subjects 200 milliseconds, but you can take all the seconds you want. And so the question now is very easy. It's a very easy question. Actually, I saw a poster that relates to that there in D. Is what letter was here? Can anyone tell me? D? Who said D? Or B? You? What? B? D. Okay. For how much money? And I'm serious. I'll take the bet to like 3-1. $1. Okay. Someone else? You? What did you see? You. You were not looking. Okay. Anyone saw a letter, that different one? L? Who said L? For how much? €5. Okay. Someone else? Anyone saw another letter? Ooh, for how much? €5. Okay. Okay, I made money today. That's good. So at least I could close here. So, anyways, so the answer is oops. Oh man, I hear this. So the answer is L. This is the letter it was. And you said the other ones. No, the other one didn't say any letter. You said B or U. So that's the error. I mean, there's a poster here by Comte and first author. And that's you. Okay, so you know about that maybe, that the idea is that when you have this in memory, we tend to swap things. So we remember the items and we remember the positions, but we swap them. And often these swaps are very high confidence. So the reason I wanted to give you this game is that you get a feeling that when you're doing this task, so it's a classical decision task, you have to respond to the letter, and the answer is B or L. But you also, all of you, the ones that did that and try to do it really, you get a feeling of how certain you are about the response you're giving. I'm completely sure. I'd bet my life on that, and often we bet our lives on things that we shouldn't. That's going to be, that, and that's going to be part of the talk. And often we respond, but we respond because we were forced to that, but we have a feeling that frankly and honestly we had no idea. So this is the question I'm interested in, not so much in what's been the classical dimension of decision making, which is how we make choices and why, but actually what's this feeling of confidence, of certainty that we get to ourselves when we've responded to something. And of course, confidence can be thought on many dimensions. People have confidence in themselves. There are people that are self-confident. People have confidence in the future, so there's people that are actually optimist and pessimism. People have confidence on things that have nothing. So for instance, I'm very confident that Barcelona will win against Atletico Madrid on Sunday. And of course, this is weird because I have no nothing that I can do on that, but still we can have different confidences of that. So people can assign beliefs of confidence, of certainty or doubt, to things that are motor actions, perception, decision, ourselves, the future, all different kind of things. And this is what I'd like to talk about, how actually we do construct this feeling. And of course, as I said in my introduction, this is a very old topic, and the way we do that is we just ask subjects. So this is our experimental device. It's very cheap. It takes $2. We ask them in a paper or in a screen to respond whether they're completely sure about something or they're completely uncertain. We also do as we did now, so wagering procedures. So we ask people to bet, or we ask people how much they would be willing to wait for something. I'll tell you there are different ways, some are explicit and some are implicit, that we can try actually to convey the feeling of certainty of someone. And I'd like to make a very brief, just one slide introduction, because I think that there is a reason that that confidence didn't make it to mainstream neuroscience for many years. And the reason is that there's been, I mean, it's related to the issue of consciousness. Consciousness also did not make it to neuroscience for many, many years. And I did make it like about, 30 years ago or 25. But before that, people used to speak about the C word, as if it were something that you shouldn't really speak about when you're speaking about serious neuroscience. And the same thing has been true for confidence. And there are two reasons for that. And so one is the classic idea that, of course, I'm at the same time the object and the subject of what's being inquired. So when I'm asking, one thing is I ask you how to respond to something. The other thing is I ask you to look inside of you and fish for something or capture something where you're actually the subject who is actually observing and also the object of observation. So this was raised by many philosophers. I just raised Comte as one of them. And the other one is I think we forgot, or maybe I think the majority of us have forgot the influence that some people have had on how actually we should build psychology and neuroscience, and that it should be in an extremely objective manner. So I just took this, I mean, this is from Skinner and Watson. You've probably all known them, and they've been, now they seem somehow old, but somehow the traces of their thoughts are still there in the way we do neuroscience. And they were, so this is speaking about introspection, so our ability to know our thoughts, to know our knowledge. But this confidence is one emblematic case of introspection. And here's how they go. Introspection forms no essential part of psychological methods, nor is the scientific value of its data relevant. Because the idea is there is no way that you can ask someone about their own beliefs. You can ask about only objective manners. Belief in its existence goes back to the ancient days of superstition and magic, formulating psychology by sweeping aside all medieval conceptions. So it's a very strong view in which so-called serious and experimental psychology should be built only on the basis of things that you can observe directly and that do not require subjects to inquire about their own thoughts. And so this is why I think that it's kind of interesting just to make an observation of the historical perspective of these things. So I want to first give you an idea of how the data looks. And I think that that's something that one would not do in any other field. But I think that this is necessary here because it may be the question that when we're asking about confidence to people, the way they respond is just very unreliable. Because we get this feeling. It may be that, Sunday morning I feel very confident and I'll give you very strong responses, but then, I had a very bad day. And so we get the feeling that psychology should be reliable. It's not. You've all heard, like 3 weeks ago, this science paper on replicability, where it was shown that about 65% of very serious papers in psychology had a very hard time being replicable. So I think that there is a real issue on when we're doing this science on asking ourselves, what's the validity of this data? Are we looking at data that actually has a genuine and robustness, like when we look at gravity or when we do really physics, or maybe when we register at oriented cells in the primary visual cortex, which they will not change the response from Monday to Tuesday and from the morning to the afternoon. They may change with anesthesia, they may change with behavior, but they have certain reliability. Is confidence of this class? Or are we trying to ask something that, on a way, does not have any sort of reproducibility? So here you have one subject, and he's gone through the experiment you saw now, and sometimes he knew a lot, and so he was very certain, and you get something that you get the feeling that you should get. People should vary widely between a sense, of course, in a task that varies between very difficult and very easy. If it's a very easy task, you should always be very confident. If it's very difficult, then you should always be very unconfident. But in a task where attention goes on and out and so on, you'd expect something like that. This is one subject. And this is another subject, which is more typical. I don't know how much you know about Argentina, but this is a more typical Argentinian, actually, at least on the way good thing about working on this in Argentina is that we have a national pathology of confidence. So it's like And so this guy on the right would be and Italians understand that, of course, and Latin Americans, we are hated, all over the world for that, and probably they're right. And so this is a problem, because, now I'm trying to do science, and I get, one subject that gives me, like a reasonable, by model, maybe a distribution that I can parameterize in many ways that I'm interested, and I get another subject that is, something like completely different to that. But of course, this is typical in biology. My brain is different than the brain of any one of you. That's different between all of us. And the way that V1, where it's exactly located, it's different. But the point is that there is a V1. So the question is not where these distributions are different. The question is whether they are reliable on a way that then I can do the statistics that I need to do to make reliable and valid science based on this data. And so this comes from bringing the subjects another day to the lab and having them play the same experiment, and these are the distributions we get. And you see that they look quite much alike. 3, 4, 5, 6, 7 days, different hours, different times. And what you get is that the distribution, and we've done this, I was going to say thousands of times, but this would be the classic exaggeration I was referring, maybe tenths of times. Many times we've done this experiment, and each time we get this idea, which I think it's the first interesting idea I'd like to present to you today, which is that the way we express confidence is a fingerprint of our personality. It's a very, very reliable and idiosyncratic thing that defines us. So if you'll be here, if you come here today and I'll measure your height, you'll have a certain height. If you come in 3 days, it will be the same, and so on. The way we express confidence, the way we report, where we tend to be very much on the right side, very much on the left side. Not only that, where we are very bimodal or spread or wide, it's a language. In the same way that you can recognize someone from behind by the way they're walking, because they have a particular way of walking, or in the same way we have a way to expressing language through words, because I speak in a certain manner, and I recognize my friends in the very moment they start speaking in the phone, because they have a very idiosyncratic way of speaking. Also, we have a very idiosyncratic way of expressing confidence. So there's a first interesting thing also, which is that confidence is a sort of language. Regardless of how probabilities are encoded in the brain, we'll go on to that. This is filtered by a readout system, which is very idiosyncratic because it has to do with the way we speak, with the way we think about things. So there's a...
What are we looking at here? Is this the amount of money you want to...
No, so this is... Yes, thanks. So this is you report on a scale from 0 to 1, where 0, your confidence. Here is explicit confidence. I'll show you...
But there's no cost to it.
There's no cost to it, and I'll show you that when there's cost to it, it's exactly the same. So people, one possibility is people don't care for that, so they could report whatever they want because there's no cost. I'll give you another slide later where people are doing that on a wagering scale, and we get exactly the same data and the same profiles and the same stability. So people that tend to be very much to the right. So it's not exactly the same because there's something, so it's filtered by risk aversion. So you may have people that are very confident, but still not willing to bet money on that because they are very much risk averse, so it's a filter that's on top of that. So there's a lot of discussion on the field of what's the best way actually to measure confidence. So one possibility is if I'm very confident, I'm going to bet a lot of money, and this is important because I really care for the thing, so I will give the best estimate that I can. Another possibility is just to get your report in a logit scale, so from 0 to 1. In our hands, this is more reliable because it's less filtered by things like risk aversion, by people, when it's about money, also people do weird things.
But there's also an anti-correlation with performance of money tasks. Are you going to talk about it as well? Or are you going to leave that out?
I'm going to be talking about something about money, and then maybe not exactly what you want, but then if I don't, then you can come back to the question. But I'm going to be speaking about money tasks, but probably not about that. So we can discuss that later if you want. So this is... So I said, those are two distributions of confidence, and I joked on that the one on the right is like overconfident, but we do not know that, because to know when someone is overconfident is when they have more confidence than they should, and what's exactly that the confidence that they should depends on their performance. If I'm always right, and so in the slide I showed you before, I discovered something. This is interesting. It goes off the, but if someone knows Argentinian jargon, they will appreciate that. There's a word here. So this is bulo. Bulo in Argentina is the apartment of lovers. So if you have a wife or if you have a husband and you have a lover and you have your apartment where you do your stuff with your lover, then this is called a bulo. I don't know the word for that in English. I don't know if there's a word for that in English, and I don't even know it in Spanish, the word for that. So I realized that in Argentina, this I did in France, the first experience. When I came to Argentina, I really was getting the right answer. And they were very confident, and so I had to change the slide because people always. So what I'm saying here is that, and of course this is part of how perception works. I mean, if there's a word here, there's no way you are not going to see it. So if I'm just asking for a letter within a word, then the task becomes very simple. So what you need to do actually is to somehow compare confidence with performance. A subject has a good introspection if they are very confident when they are right, and they're very unconfident when they're wrong in a first choice. This is what you would want to know. And you can translate this to life. People do well in life when they bet very strong, when they have good reasons to do so, and when they bet very mildly when they do not have the reasons to do that. So it's not just high or low betters, it's how it relates to knowledge. You could think again, just to give you a feeling of this is very classical in school. So you all went to school, and you know that you had a friend that typically went on after an exam, and you said, well, how did it go? Horrible. Very bad, I had no idea, it was a mess, and then they got a 10. And not only that, I mean, it was the 14th time that this happened, and so you could ask him, why don't you learn from evidence, as you know, and reinforcement learning and all the mechanisms that we have for updating information? If 40 times you thought you were wrong and you were right, why don't you change your idea and you think that maybe you'll be right? I mean, if you had 40 samples of evidence to construct that, and you had the other people, the people that actually, it was great, fantastic. I gave the best exam of my life, 2. I mean, 2 out of 10, right? I mean, it reminded my cousin that actually came very happy because he had a 10, but it turned out it was a 10 of 100 and not 10 out of 10. So of course, all these there's also the issue of scaling, which is pretty important. So what one wants to know, the good student is the student, I mean, not the good student, the good introspective, the good student with good introspection is the one that after the exam has an idea of how well he's done. If he did very well, he should bet high on his exam. If he did very bad, he should bet low on his exam. And this is the idea that I want to address. The question is how we measure that. And this is very simple, like statistical analysis. But since this is a course, I'd like to guide you on that. Maybe you all know that. And it's going to, like, how you build a receiving operating curve, which is the way of measuring that. But I'd like to guide you on that just for pedagogical reasons. So imagine that now I plot on blue the confidence on the trials that you were wrong. And on red, the confidence on the trials that you were right. And this is a subject that I will call, this is a subject that has a good introspection. When he's doing wrong, he doubts of himself. He knows when he's doing right, you know, he's very confident. This is a subject that I said has a very lousy introspection. Do you follow me on that? Is that clear? Are we all together? Or yeah, perfect. Okay. So it doesn't matter exactly the shape of this. I don't want to do any parametric test because he could have whatever distribution he wish. The only thing that it's important is that the distributions for correct and error trials are somehow separated. If he wants to be very optimistic and shift this entire thing to the right and have, you know, the error things here and the correct things here, this is perfect. I don't care. That's his own language, whether he likes to speak with more positive or negative adjectives. What I want to know is whether from his language of confidence, I can infer his performance. And if I can do that, that means that he's a good knower of his own knowledge. He knows when he knows, and he knows when he doesn't know. The one on below has no idea of his own knowledge, so has very bad actual introspection. And so the way for doing that is actually an RRC curve, which actually works essentially like this. You just get, I mean, the issue with this is that it has to be no parametric, because I don't know if these are Gaussians or exponentials or whatever distributions they wish. So you just, but the idea is very simple, and I'd like to explain it to you. So you just get a slider that starts in 0, and you first ask the question, how many trials do I have that for which the confidence in the blue distribution, in the errors, is beyond this line, and the confidence in the red distribution is beyond this line. And of course, it's 1 for both and 1 for the other one. The entire distribution is to the right of 0, because it's forced, the confidence is always positive, and the entire red distribution is to the right of 1. So these two distributions these two numbers are 1, so I start here. And now I'll start moving, and I will see how I'm going to be crossing this distribution. So I move to the right. When I move to the right, what happens is that I'm going to start going on the, notice that for this, it didn't matter if it was like more to the left or to the right, but I start hitting on the blue distribution, I start passing on that. So these points start moving on here in this direction because the number of confidence that were to the right of this number has decreased, but not for this one. And I keep on doing that until I hit the point in which there's the border between the two distributions, and then the other distribution starts going down. So what you get is that if these distributions are completely separated, it doesn't matter the shape they had, I will be surfing through this line until I hit the red distribution, and then I will start surfing from this line here. If these two distributions overlap a lot, then what I'll get is that as I start moving right, you know, I will going down in the mode of the two distributions, and so I will be much closer to the diagonal. Actually, if it will be crossed to the other side, that people have higher confidence for error trials, then I will be going on this side and this number would be negative. So what then you have to compute is this area here, the amount of area that is above the diagonal, and this is the area of the ROC curve. And that gives you a number of how well these two distributions can distinguish one thing. It's a classifier. It's a very simple classifier that can tell you that. So this is a very simple, non-parametric way of actually inquiring whether someone has a good introspection or not. And once you've done that, you can ask, okay, now you can run a task. So this was done by Steve Fleming in England. He had people doing a very simple perceptual task. He didn't care about the perceptual task. Then he asked for confidence. And then what he saw is that some people were very good, reported confidence very well, in the sense that I just said. When they were right, they had high confidence. When they were wrong, they had low confidence. And some people were very lousy. So the question is there something in the brain of the people that are actually that have very high precision in the confidence system, and people that have very low precision system? And he made a very simple regression on that. And what he found is that there is a region, very focal region, on the right frontal cortex called the Brodmann area 10. This is the Brodmann name for it. Where what he found were that there are a number of anatomical markers. There was no functional study here, which included the size of the gray matter and also how well this region was connected to other regions that predicted. You see, it's not a huge correlation, but the prediction was reasonably well. The area, so here's the area on the receiving operating curve, so you could think how good they are in assigning confidence and this region of the brain. So this is reasonable, because if I started saying confidence is something that's very idiosyncratic, then there should be a strong biological anchor that would be able, that we could say, I can predict from some biological marker whether you will be a person that has good way of assigning confidence or not. So this was Steve's paper. Then we somehow followed this up on a study that I want to share, because I think it has an interesting idea also. First, it was functional. So it's a complex study, and I'm going to go really fast through it. You can ask questions if you want on that. So what we did is we measured brain networks in stationary fMRI. It's not resting state. Now I'll give you the data, but it's stationary. So we asked how the brain is functionally connected on a state in which somehow doesn't change through time. And we did that. So we broke that into according to standard regions. And what you see is that, and then we measured the correlation of what's called type 1, so the performance. So this is the same task you actually saw for this one on the letter task. And type 1 is how well people do on performance. This is not what we're interested. Then we ask what's called type 2 performance. So type 2 performance is is the short name for what I just referred, is your ability to assign confidence well. A person who has very good performance has very high confidence when they're right and very low confidence when they're wrong. A person that has very low type 2 performance, confidence has nothing to do with performance. And so what you see here is that there is already a very distinct pattern. This part I'm not going to even tell you because it doesn't matter very much. These three things here, this is a bit different from how classical stationary MRI is done. We had subjects come to the scanner, and we had the new resting state, so this would be the classic thing here, and you see that there's not much on how the brain is connected. So red arrows here mean that the people that have good introspection have stronger connectivity than the people that have bad introspection. So how much this connection is a proxy or a signature of whether this person will have good introspection. And you see that in resting state, there's not much. What we did in these three states is we had a small library of mental states instead of just having one, which is resting state. We asked people to concentrate, just to do resting state, so do whatever you want and just let your mind wander wherever it should be. Then we asked people to concentrate. I mean, for all of you that have been in a scanner, who of you have been inside a scanner? Not that many, actually. I thought it was maybe more. But you know that there's a lot of noise out there. And actually, one interesting way of being in this, if you ever go to a scanner, one recommendation is concentrate on the music, because this makes the experience much better. It's a very strong, loud, and rhythmic music. And you can just concentrate there and try to find patterns. And you're driving your attention to the external world. Part of the thing that is very anxious is that when you're in the scanner, the attention is toward your own internal state, and this can be generate a lot of anxiety. One solution to deal with that is to concentrate in the external world, just listening to the sound. This is what we ask subjects here, just to try to concentrate on the noise of the scanner. And the subjects here, we ask them to concentrate on their respiration, on their breathing pattern. So you could think of this as this was no meditation, no meditators, but so this is called interoception, which is driving your attention to internal states of the body. So here you have how and what you see is that it doesn't matter if attention is in the outside world, wherever it goes through like spontaneous fluctuations, or in the internal world, the patterns that predict whether someone is good in a visual task or not do not change. Now, when we look at how patterns predict your ability to assign confidence in a decision, they're completely predictable when you're doing interoception, but they're not predictable at all when actually when attention is driven to the outside world or to or random fluctuation. So I think that there's a second important idea here which I'd like to convey, which is confidence, confidence, for being confident or not, this is the idea I'm trying to convey today, is you have to look at your own thoughts. You have to estimate your own knowledge. And what I'm showing here in this slide is that looking inside, whether it is to your body, to your respiration, to your cardiac rhythm, to whether you're well or not, engages very similar systems and becomes idiosyncratic, reflecting the ability to actually thinking about your own thoughts. So there's a relation when the mind thinks inside. It doesn't matter if it's to your own thoughts through confidence or to actually body states, maybe thinking about your respiration.
But then you mean this in terms of metacognition, or you mean it more specifically for conscious awareness of?
Well, yeah. So this is a good question, and the answer is I don't know. So confidence can be expressed in different matters. In all our reports of confidence, and I would say in the 99%, maybe more, of the studies that you'll find on confidence in neuroscience, they're conscious reports of confidence. So what you're saying is your willingness to report whether I'm confident or not, your willingness. So there's a question, but there are other manifestations. So for instance, when you're with someone, you know if they're confident or not on something, maybe by their posture, or maybe by the time, if many of you probably have been professors, and you can say if your student is confident or not by the way they tremble with the voice. So the question is whether, if I were to measure these unconscious and implicit body markers of confidence, and the answer is I don't know. I think it would be very likely that this is specific to a conscious and metacognitive representation of internal thoughts. But this is a very good question, and the answer is we don't know. We do not know it. They do correlate. So people that are actually not only that, but they help. So a way to improve confidence is actually to help people actually detecting. It happens like with emotions. Often we express emotions and confidence more in our body than our explicit thoughts. Yes.
Yeah, but thanks. But the model that you're talking of, you're kind of assigning the same weight to my confidence and when I in fact succeed.
Yeah.
And I say I'm wrong, and when I fail, but I'm saying I'm
Yeah.
right.
Yeah.
But this might be pretty different, due to different social stereotypes and things.
Yeah.
Like that. I might have different weights. So to say that I was right when in fact I was wrong might be worse than to say that.
Yes.
Yeah.
Yeah. And you're right. And not only it varies with. So this varies. I didn't say that, but actually, confidence varies a lot with cultures, the way they express. And I think this is related to this kind of issues. So how people in different cultures feel about saying that they are right. So it's preferences of, if I'm in doubt, I prefer to say I don't know, or I prefer to say I know. So yes, you're right. This also varies not only on that, but it also varies on the specific task. So in different tasks, I can give different payoffs so that errors for not being sure when you should or for being sure when you shouldn't actually have different costs. But this analysis doesn't care that much about that because I'm splitting. I'm just asking whether these distributions are different. In this particular analysis, I'm not in this particular one. I do not care that much about where they're all shifted to the left. So typically you tend to say I don't know, or typically you tend to say yes I do. The only question is whether from your own expressions of confidence I can separate when you were wrong or right. So if what you are saying is when I'm doubt I will say always zero confidence, then you will be your type 2 performance is going to be very low by definition. So I'm not giving specific weights to either one or the other one in this task, but actually we do, and I'll show you a task in 5 minutes where we're actually shifting the balance between these two things. Okay, it'd be great if you ask more questions. I know it takes, but thanks. I mean, because then I'm going to speak less, which is going to be great for you and for me. Okay, so in the Fleming paper, with actually I didn't tell you the task, it doesn't matter, but it's a orientation detection task with two different. You have to say there's a grading that changes, and then the question is whether it changes or not. And in our task here, which is the letters that you saw, we are, and this relates a bit to your question, we are making points about how people assign confidence, but just on one particular task. And the question is whether, I mean, this is maybe whether we should change our titles and say, this is what happens in the brain when people are assigning confidence well in this task, or whether if we do find it in one task, it's more or less similar to where people would find it in different tasks. So the question is, and this is awfully reminiscent to an old literature of general intelligence. The question is whether, if I do find that someone, or emotions or anything, the question is if I found a property of someone, inquiring on a given task, and I said he's strong on X, he has this profile for emotions, he has this profile for intelligence, he has this profile for confidence, he has this profile for memory, is whether this will actually translate to a wide variety of tasks, or whether it's something which is completely specific. So actually different people, we, among others, did this study, and this is what you see here. So this is one study in which you have like an auditory task, in which you have symbolic tasks, you have luminance. This one I'm going to be talking different, but different kind of tasks. And what you have is the degree of correlation between, someone comes to the lab, they do a visual discrimination task, we measure their precision in the confidence system, then they come and they do an auditory task and we measure the precision in the confidence system, and then this is one point and we see whether they correlate or not. And you can see that within tasks, through different days, the precision in the confidence system is reasonably good. These are the points here, and this is, you see the statistics of the Pearson correlation. When you change across tasks, and you take all of them, there is still a significant and somehow strongly significant correlation, but you get the point from the dispersion of the data that this is a very wide distribution. So the capacity from someone to saying you're a good introspector based on one task and how this would translate to other tasks actually has a very strong variance, a variance that actually is on the order of magnitude, or even better, even larger than the effect size we are seeing. This is different.
Across these tasks, can you really say that you're operating at the same level of difficulty?
Yeah, so all these tasks, this is so these three tasks are all fixed at the same level of difficulty by definition, 75%, and this one is free. So we also varied that. We varied whether there is these numbers should not change in difficulty. This is the important thing. They should not change, but because they could. In this task, we had two different conditions. One in which performance was fixed and we changed the signal, and the other one, the signal was fixed and we varied performance. It's part of what we varied across all these tasks. So I mean, it is consistent across tasks, but I want to give you the right feeling that is consistent with a lot of variance. And this, I think, it's the same summary for general intelligence. People, I mean, and this is a very old and difficult problem. If you try to estimate intelligence for someone, you'll find that first, it's very hard to define. It depends what class of intelligence and so on. But then the variance is actually extremely large. Now, it becomes extremely different and much more precise what you measure is not the precision of the confidence system, but more where you're shifted to the right or to the left. Whether you try always to say, I'm very confident, regardless of whether I was right or wrong, or I'm very unconfident, regardless of whether I was right or wrong. So how it separates one and the other one is not so precise, but where I stand is something that it's almost, so in the same task is what I showed you before with all the distributions. So here's only the mean, but the whole distribution and any parameter you estimate is almost the same. It's what I said, it's language, and this is something that's extremely reliable across tasks. So summary is people have a very idiosyncratic way of expressing confidence, which has a somehow idiosyncratic also precision, but that may change from one task to the other one.
But I'm getting a bit confused because if you look at it, it looks correlated.
Yeah, this is very strongly correlated.
Right. It's another, but then you say it's a language, but it's just a correlation. I have some subjective state I can report to you that correlates with my performance.
Yeah.
So what makes that a language? It's just that I have a metacognitive state
well,
that sort of reflects my level of
I'm going, so by a language I'm saying that you have a way that the distribution that you choose to respond to confidence is almost always the same. So this is what I'm saying, what I'm calling it.
It's a scalar. It's just a scalar.
It's just a scalar, okay.
That's not language.
Okay, not from this data. I'm pushing it too hard. But since you brought the question, there's also language. And this is, I think, also brings to a very important issue. You all go to the doctors. And the doctor will tell you, like you have X. And then you tell the doctor, well, should I do this treatment? And he says, yes, if you do this treatment, you have it's very likely that it will go well. And the question is, what does very likely mean for this person? Very likely for him and for you may mean very different things and means different things in culture. Same for a judge. A judge will go and say, well, it's almost certain that this person did, and the question is, what does it mean to be almost certain? So many people have done actually calibrations of language, and what you find is that these dispersions in Scalar actually also correlate with the words people use to express confidence. So there comes language. And you also find that people actually, when I'm saying I'm sure, maybe it doesn't mean the same thing that when you say I'm sure, it doesn't mean the same thing that...
The point, if you look at the dispersion redistribution, it is not as extreme as we started out with, because you started out with examples where you had the Argentinian versus the rest of the world,
Yeah.
which was very extreme.
Yeah.
But now we have sort of a modulation around some average. It's
Yeah.
just, so I could argue, well, that's a detail. So if my doctor says, well, I'm rather sure, plus or minus 10%.
Yeah.
If you look at this.
Yeah. So what I'm saying, it's not the case. When you look, so I don't have this slide to show you now, but I'm telling you the data is if you get the same problems and you give it to different people, and you rank what words they use. Now it's words, so it's really language. You will find that there is a very strong difference, and this difference is also very persistent and reliable. So what this builds is a problem of communication, because you go to the doctor and he says, I'm sure that this is very likely to go well. For you, that means 90% probability. For him, it means 65% probability.
Sure, but you agree with this data, we cannot draw that conclusion yet.
No, not from this data. So that's why I'm giving you the other one. That's exactly what I said. Yeah, I overpush this a little by saying a language. And since you bring this to the table, I'm saying the reason I did that is because there's other data which I didn't bring here to the table, which I'm bringing now, which combines to this actually to give the idea that this is something like language. I'm trying to make it. Yeah.
Wouldn't it be better to say that you are looking for syntactic invariation?
For?
Instead of syntactic invariation.
Syntax.
Say, you don't change semantics. Instead of say that's a language, because language there's a lexicon and there's a semantic.
Yeah. Okay. I mean.
It's more like you're ensured that this target has a kind of no statistical variation.
Yeah.
It's not a language.
Yeah. Okay. Let's forget. Okay. Point taken. It's not a language. I mean, it was a metaphor, and this is the issue with words. I mean, we are here with the exact same problem that I'm trying to present. When I'm saying it's a language, I'm thinking about something, and it may not be the same for a linguistic, and it may be the same thing. So, which is the same problem that I'm raising here when I'm saying someone is saying I'm sure about something. It doesn't mean the exact same thing, so it needs translation. But by here, what I try to say is that it has a feature which is a very idiosyncratic way that we have to express something. It's a very idiosyncratic manner of expressing something. Yes?
I have a question.
Yes.
Regarding the different kinds of tasks.
Yes.
Do you think that there can be some kind of relation between the confidence that, for example, someone felt in the auditory task and their perception of themselves, in the sense of, for example, if I say, I'm better in auditory tasks than I am in luminance tasks.
Yeah.
Will this change my confidence regarding my
yeah,
answer?
It does. So well, first thing is that one thing that I didn't show here is that what you see here is that there is a strong correlation, even if you go to different tasks, in where people tend to be in a confidence line, where I tend to be. This translates to very different forms of confidence. So for instance, there is a very standard optimistic test of optimism, where you give people problems and they tend to respond, and you can rank them on people that tend to be more optimistic or less optimistic. And this correlates a lot with that. So decision in a completely so-called abstract task that you've never done, auditory, very technical in the lab, where you try to stand has to do with decisions in other sort of tasks, but also with very different domains that you may be familiar with in your life. So with general general knowledge problems. So there's something which it does not depend on what you are saying. It's more specific. It's something that actually, it's a general tendency of a person to feel, or at least to report, as more confident or less confident. This has a lot of translation. Then, of course, there's the issue of domain specificity. First, because there are some genuine things, although we try to, it's a difficult technical thing to explain, but this analysis should be independent of performance, but they're not completely independent of performance. So for instance, if imagine that I give you a task in which you have completely no idea, like I'm giving you, so you will always say, I don't know, and you're right to say that, so it's a very easy task in terms of introspection, because you know that you don't know. The same on the other way around. If I'm giving you mathematical problems, like 3 plus 2, 2 plus 4, you will always respond correctly, because you're certain that this is right, and introspection is going to be very easy because you know that you're always right and you will respond with high confidence. So there's a regime in which if you're either very high performing or low performing, these things become unstable. And so we need to work in regimes where people are far from perfect, are far from completely wrong, to be in the dynamic range where we get the best measures. And above and beyond that, there's the issue that I think that you're raising, which is the perception that people have about themselves in different modalities. So the idea that I think, maybe I'm not so good at music, but I think I'm good in music, and the question is how this affects that. And this last bit, I don't know. I agree with you on the intuition that it should affect, that there should be different contamination based on biases which are task or domain specific, but the answer is that we've not done that, so I cannot answer it. Yes, question?
What are the variables that we are looking at in this slide and the previous one?
So what you're looking is you get so in this chart is the average confidence reported. And what you get is, so this is an auditory task where there's a tone and there's a second tone, and then you have to respond whether the second was higher pitch or lower pitch, for instance. And it's on the border of like 75% performance. So we keep it dynamically so you'll be there. And then you do many of these tasks, and then you respond whether you thought you were confident or not. And then we do, as I showed you, we can so in this task there's no accuracy, and then you respond confidence, and we look at your confidence. Like your average confidence. Maybe it was 85% for one subject. Then you come in another session and you do the same task, and we measure the same confidence. This is confidence for one task, and this is for one session, and this is confidence for the other session. And what you have is a scatter plot where each dot is a subject, and you're plotting average confidence in one session versus average confidence in the other session. And on red here, those two sessions correspond to the same task. And you see that if I came one day and my average confidence, first thing you see is that the average confidence changes through task, and this is normal. So here, they're lower in the diagonal because this is a more difficult task, so people overall feel more unconfident than in this task where they have better performance. Also, you see the answer to your question in that, which I had never seen before, which is that although the performance in these two tasks are the same, people tend to be more confident in this task than in the other one. So there may be something here where the different domains separate, where you may feel that in a visual task you do better than in an auditory task. Never thought of that, and now you raised me to this. And so in these items here, what you're seeing is what is the stability of the average confidence if I come one day and if I come, so it's the quantification of the slide I showed you first. And you see that this correlation is extremely tight. What you see here again is the point for all sessions, and you see that they are close to a pre-cell correlation of close to 0.1. Here what you have is average confidence when people come to do like an auditory task here, and you measure the same average confidence. Then they come to do a contrast discrimination task, and you measure the average confidence, and you plot that here. Again, each dot is one subject, and so now they're completely different tasks. So you could say, I may be very confident in one and very unconfident in the other one, and you still see that despite the fact that they're different tasks, the correlation is quite strong. Okay, so what you're plotting is the stability of this measure across these different sessions in a scatter plot. Is that clear? Yeah. Okay, perfect. You said in the slide before, it's exactly the same structure of data, only that the observable is not the average confidence, but the precision of confidence to separate right from wrong. And what you see here is that the correlations exist, but they're much weaker. This is the point I'm making. And on doing so, I'm criticizing a literature which is pretty vast, including ourselves, which makes the claim of, for instance, the right frontal cortex is the region which is involved in metacognitive accuracy. I think that this slide raises a question that if you're making this claim, you should understand that this depends a lot on the task that you're using to probe metacognition, because the correlations exist, but they're relatively weak. So I think that claims that people have made, including ourselves, of this region is important metacognitive accuracy, should acknowledge the fact that actually this estimation varies widely if you measure that from one task to the other one. Not the same, and it's quite different, if you want to measure what's the bias in confidence that people have. Yes?
The variables on the previous slide is?
The variable in the previous line is the area in the receiver operating curve that I showed you before. So you measure how someone, so it's an estimate of whether the distribution of correct and error trials are separated. If they're completely separated, it will be a very high number. If they're very overlapped, then it will be 0. You're measuring how separate the error and correct distribution, the distributions of confidence for error and correct trials are, which is what we call metacognitive accuracy or precision of the confidence system. So this is the precision of the confidence system, and this is the bias of the confidence system. Bias is very stable, precision not so much. Okay? Thanks for that. I'm going fast because I got a lot of stuff, and those are important details. I thank you for bringing them. You know what? I'll skip this, and because I want to have time to give you a bit of two more stories. The first one is, so here's money. You were saying, I mean, how this relates to money, and here comes money. So, so in the majority of the tasks we use, as in a lot of neuroscience, are tasks in which we have a well-defined decision variable. So, for instance, in the contrast discrimination task, or in the pitch discrimination task, the decision variable is just the difference in pitch between the two tones, and it's an external variable that we can measure. In the majority of real-life decisions, we do not have a good handle on what is the decision variable. So when you buy a house and you're choosing between the two of them, and you decide, okay, I'll buy this house, and you bought it, but you left out with a feeling of I'm not sure I should have done that. It's hard to know exactly there what's the decision variable, but there is an idea, it's the main idea of economics and the main idea of neuroeconomics, that all this intricated and complicated stuff can be grouped onto something that we call value. It's the value that someone has, and it's the amount of money that they're willing to pay for that. Of course, there are a lot of critics to that, but for now and for these 3 slides, I'd like to hold to the idea that things do have a value, and that value may be a good proxy as a decision value for decision problems where the decision signal is actually not so directly defined by external stimuli. So this is a study by De Martino and also by Fried and the other people in Dolan and so on, the people in UCL, and this is what they did. Now you have to choose, and it's not choosing between high and low contrast, but you have to choose between candy. So you may choose between this thing and this like between these two ones here. And is it raining or someone is having a shower? Or eh? It's a storm. Interesting. Are you sure?
No, it's a jacuzzi for after the talk.
Okay, perfect. Okay. Yeah. So then again, you give a confidence rating on your choice, and then after the scanner, what you can do is you can say it's a typical bidding task where you can say, well, how much money am I willing to pay for the object that's here? And so the idea is that when you're making a choice, of course, this is an internal representation, and of course, this will change. How much is worth a glass of water is not the same thing if I haven't drink water for hours than if, but overall, accepting that this has some volatility, there is some stability, at least in the range that this is studied, where value has some persistence and where one can study these kind of things. And so the idea is that the difference in value between these two things should be a marker of decision. People, when they're given 2 choices, should opt for the one that they're willing to pay more. And this is what happens here. This is the sigmoidal curve that you see here. What you get here is what's the probability of choosing the item in the right. And what you have here is the difference in value normalized between the item in the right and the item in the left. And you see that you get a typical sigmoidal curve, like in any other decision problem, where when you're giving a choice, you'll tend to opt for things for which you would be willing to pay more. So this is essentially just a validation of the idea that value is a good proxy for decision maker. But when people actually make these calls, they also doubt. Sometimes they are sure. I mean, I'd rather have 10 kilos of something I like than 2 kilos of something that I do not like. But often you have to choose between things that you say right, but I'm not so sure. And so if this were true, then this should reflect the uncertainty in value. The idea that I'm not sure, so this thing has a value, this thing has a value, but of course value is not one scalar, it's a distribution, and the uncertainty that I have, which is expressed in confidence, should be an idea of the measure of errors that I can make. And so in the gray curve, you see the high confidence trials, and in the black curve, you see the low confidence trials, and you see exactly this idea that there's much more variance. So you could just model this as assigning that confidence is giving actually the uncertainty on the estimation of value. And skip that. And so now again, the question is what's happened in the brain. And so there's this region that has been studied for so many studies and years and people where you do value based decisions, and you find that there's a region here in the ventromedial prefrontal cortex that actually responds to the value of something. So this region will respond more when you're making a choice that has more value. It will respond more when you're comparing to something that has more difference in value. And the first thing I think that's nice in this study of De Martino is that what you have is that, so now here you have the things that have a low confidence are in gray, and high confidence are in black, and high confidence are in gray, and you have low value, high value, low value, high value. And what you see is that actually this region of the brain that was thought to code for value is doing so, but in a more interesting way, which is not just the scalar amount of value, but is actually weighted by its uncertainty. So if I have something which actually has a strong value, but I'm very uncertain of, then actually the ventromedial prefrontal cortex will respond in a different manner. So you could think that as your certainty that the decision is being made correct. So to make it, again, to put it in other words, you could think that what the ventromedial prefrontal cortex is encoding is the likelihood that your response is correct, given that you're choosing to something that have different degrees of values, but this value also have different degrees of uncertainty. And this uncertainty is encoded by confidence. So this is interesting, but the second more interesting part is that there is also a region of the brain which is very close to the region I showed you before. So it's in the right prefrontal cortex, that's less medial, it's in the right prefrontal cortex, that doesn't care so much for value, actually doesn't care at all for value, but just cares about the confidence. So independently, if I'm making a decision that has a very strong difference in value, a very low strong difference in value, this is the region that actually correlates very strongly with how I'm expressing the decision. So this, I think, it's an interesting circuit of a region in the brain. I will not have, we have this data also at the scale of neurons, and I will not have time to present it to you. But I'd like to give you the idea for that, which is the following. The brain, one idea that many people have, and it's like probabilistic population coding. I'm going to go fast through something that should take half an hour, but I'll try to give you the gist of that in 30 seconds. Is that cortical circuits encode probability distributions. So this is done even from orientation of something. You have a lot of neurons, and these neurons are encoding. Each neuron is contributed to encode what is the likelihood that the orientation of a neuron will be tilted to the right or tilted to the left. And the same thing is true for, so the idea is that neural circuits have an internal and maybe implicit representation of variance, of the likelihood of something, of probabilities. So one idea I think that comes from this study is that what this region may be encoding is these probabilities. Now, at some point, and at some point we need to express these probabilities by saying, consciously, by often with language, saying, I'm sure, I'm not sure, I'm certain, with a number, with a wagering procedure. The way it should be, we are asking to look in our brains and fish these probabilities and convert them into a number. This readout system may not be very precise, and maybe the reason, I'll talk about that now in 5 minutes, why often confidence reports are very lousy, why people tend to be lousy reporting confidence. So here appears an anatomical structure, an anatomical projection, which is one, it's not the only one, but it's ventromedial prefrontal cortex to the rostolateral prefrontal. The names do not matter, but the idea is that it's a circuit that encodes the probabilities, the likelihood that I have of making the correct choice, and a region that is trying to read these probabilities to convert this into a statement. A statement for myself, I'm sure I should do that, I do have to do it. Maybe a statement for the other ones, like to convey, I bought this, you should buy it, it's really excellent. So it could be, but it's a way of actually reading it and converting to a system. If it were that this readout system is actually the way that the brain has to convey the internal probabilities it represents, then these connections, as a very macroscopic and weak marker of fidelity between a system, should be a proxy for what I told you before, which is the precision of the confidence system. And this is exactly what happens. So if you rank people as the people that have very good introspection, the people that had like a separate, their confidence separates correct from wrong, high ROC curve, and the people that have a very small ROC curve, if you separate them and you measure the functional connectivity between these regions, you find that this in this task is a predictor of this value. So I think that this is maybe again a summary of a slightly much more complicated issue, which is the idea of how we compute variables of uncertainty and eventually how we read them out for report to ourselves or for the other ones.
In your interpretation of the ventromedial prefrontal, in something can you really dissociate confidence from your predicted reward? Because
No.
This is the problem, right?
Yeah, yeah,
Because
yeah.
I can also argue all that happens in ventromedial
Yeah.
is I make a statement of my predicted reward, and it actually implies, of course.
Yeah, I agree, and I'm not that, but it's, I think at this stage this is only semantic, because if you want to calculate estimated reward, what you need to have is an idea of the value, of the difference of the value of each thing, and the probability of that. So imagine you just have imagine there's no uncertainty in value. You only have uncertainty in the outcome. So you know that there's a choice that will pay 100 and a choice that will pay 10. And you know the probabilities of getting either of them. So you can calculate the expected reward.
No, but the key thing for me is just to say, it's not automatically dissociated. It's not you have two variables in that area that being combined. It might just be implicitly encoded in one.
I agree. I agree with that.
Okay.
And again, as I said, this is at a very large macroscopic scale, so we cannot make strong points of what neurons are encoding by no ways. In some regions, so let me give you because I'm skipping some things. I think this is another important idea which comes here and I'd like to present. And is the following. I think that there's a tension in neuroscience in two different fields that both of them have been very successful. For those of you that are aware of all the neuroscience literature which I referred before, of probabilistic population code, one thing that has been a landmark is the following. If you have to make a decision that's based on two different sources, for instance, you have to make a judgment about orientation and you're using haptic, tactile information, and you're using visual information. And you have to make a call that combines both of them. The problem is that, not the problem, the computational aspect that makes this decision very interesting and rich is that these two sources of information have very different reliabilities. One is very precise, the other one is very imprecise. So the question, and this comes when, imagine we are making joint decisions. Let me go out of this because I think that this goes in the interesting direction. Imagine that I'm working with you and we have to make a joint decision. They give us a problem. And so you have an idea, like they give us a problem, like what's this, how many people live in Latin America, for instance? How many do you say people live in Latin America? Fast. Let's say, 300 millions. Well, I would say 300 millions also, but I would, let me say 550 million. I'll say 550 millions. And so the question is so now we have two sources of information, and probably we can do something good with the fact that we are two, and then we can be four, and so. And the question is how we combine our information. One idea would be simple. Okay, let's average it. Let's assume that we are independent, that you have some noise, I do have some noise, we both. Now, another idea would be that I talk to you and I say, well, how much do you really know about this problem? I'd like to know your certainty. And if you're very certain, because you study geography and because you happen to have as a hobby the populations of continents in this, then I'd really like to go for your opinion. So you understand the idea that if you have two different voices and you need to put them together, you need to know the reliability of each one to know how much you're weighting them to come up with a joint decision. This happens exquisitely well in the brain when we're doing this multimodal integration. If any of us needs to make a choice which is based on auditory and visual information, we combine them very well, taking into account the boats of each one, what they're calling, but also the reliability of each one of these sources. And so this has been very influential in neuroscience as the idea that the brain is very good in calculating distributions of probabilities and using them. Now, okay, this is fine, and again, this could be, if Alex Pouget would have come here, many people would have give you this talk, and would have 1 hour actually or Walpert, or many of these people could have given you this story. But this story has a problem, which is mostly ignored by these people, which is the following. Other people, which are also very intelligent, very smart, have come from another field, which is behavioral economics, and the conclusion they've derived, it's exactly the opposite. They've worked, and this is something that, so again, it's an interesting question because you get two different pictures. Both of them are very reliable, both of them are well done, but they give the exact opposite conclusions. If you read someone like Tversky or Kahneman or any of your favorite behavioral economics, the point that you will get is that when people have to assign probabilities, they're often, all the time, completely wrong. And this is a very serious problem in real life because doctors do not understand why they need to give a drug or not because they cannot compute the real probabilities when they have to combine two things. So here are the two extremes that I'd like to present. The brain is extremely good in computing probability distributions and using them in implicit tasks. The brain is extremely bad in actually expressing this distribution. So what I'd like to give as an idea, and if I have time, I'll dwell more on that. This would be the next part of my talk, is that maybe there are regions of the brain that have all this information, which is encapsulated about the probabilities. It could be the probability of reward, it could be the expected value, it could be the probability, the reliability of the source, or so on. But when we need to speak about these things, we do not have the direct access to our MT or to our V4 or maybe into our to ventromedial prefrontal cortex. We have a very partial access, and so when we have to, and this is why I tend of thinking about it as a language, in the idea that it's a rudimentary and erosionated version of a whole probability distribution. So I'd like to me this is the key idea, is the brain is very good computing probabilities. They are there. If we could read them, then we would be very good at assigning confidence, but we are not trained onto looking onto this part of the brain and expressing them in a reliable manner, and this is what brings the problem in behavioral economics. What time is it? It's 1:30? 1 o'clock. Okay, so I'll take maybe 15 minutes. Well, I have half an hour actually, right? Yeah. But I'll try not to take the whole half an hour. To give you one concrete example. Well, let me give you the other one actually. I'll skip this. This was I like this because it had neurons and all that. But I won't give you this, all that, blah, blah, blah. There's your work, Andrea. So some of this work was done with Andrea and Sabato here. Monkeys, neurons, they were there. I'll skip all that. And I'll just skip to the conclusion of the study, and I'll give you the other one, and then so it will take me 10 minutes, and then if you wish, we'll also have time for questions. So I'll go to the second example, which is much shorter because we don't have the whole study. So one example in behavioral, what I'd like to give you now is a feeling of why this may happen. So one thing in behavioral economics, one thing we know is that confidence is usually assigned in a very wrong manner, but not just that it's noise. It's not just like you get your probability distributions and they're completely corrupted by noise. They're very stereotypical errors. So there's something in the way we read out confidence that it's biased. It's biased in a way that makes us have certain things like overconfidence in certain domains and so on. The first one I was going to speak, and I think for this we have, but this is most of it's published, and the last one I think it's maybe newer and more interesting, and especially this one is longer. The first error is what's called confirmation bias, or the halo effect, or so on. So for instance, you know that, so these were very, very famous studies where, I'll give you just one example of this, which is I think the nicest one, which is Todorov study in Princeton, which is the following. Imagine that you're giving an election, like there's an election in Asunción del Paraguay. Who knows Asunción del Paraguay? No one knows Asunción del Paraguay. Perfect. Okay, then this is a good choice. So imagine that there's the election of majors between Asunción del Paraguay, and I give you the two candidates, and I ask you who is going to win, and you see their faces. Then you're right on average on like 60, 62, 58, 60%, let's say. And if you think about this is completely weird and strange because you don't know where Asunción del Paraguay is. You don't know what are the political issues in Asunción del Paraguay. You don't know anything about these candidates. You don't know anything, but the only thing you know is their faces. And faces are a strong enough proxy to actually estimate the real outcome of an election. This is Todorov in Princeton. To me, this is an extremely, I think that this should raise a completely change in how we organize our current elections. This is a very serious issue on how we are actually electing. And this is something very simple called the halo effect, which was studied mainly in Israel, but by many people, by which when some person has a virtue, in this case, a face of being trustable, or a face of someone that seems to be a good leader or something, whatever that is, but that's something that is very reliably perceived, then people extend this to other judgments. So the idea, and the classic idea is given, is if I tell you that there's some person that works a lot, is very hard, is a very courageous person, is tenacious, is very driven by passions, and is stubborn, then stubborn, you will think that's a compliment. And if I tell you that someone that actually doesn't work very much and actually doesn't change their opinions and is not flexible and stubborn, then now stubborn, which of course is ambiguous, you will take it negatively. So the idea is that once you've made opinions about something, You try to convert information so that it confirms the opinions you have, and you do not bias like just information equally as you should. This is the first typical error in confidence, and I think we've proved that we understand why going very deep into neural circuits, actually the brain actually makes this type of errors. The way we make Bayesian inference actually results in this type of system. And the other one I want to show you is a second one, which is, this is the classical example again. So if you tell people in a telephone poll of 300 seniors, 70% support the president. This is the classical Kahneman example. Then you come 1 hour later and you tell people what this statement said, and people think, well, that 70% of the people support the president. And what people have forgotten is that the reliability of this, whether it was 300 people or whether it was 10 people or whether it was 1 million of people. And if I tell you, if instead of this I give people, imagine this is an election of 3 million people, and I tell them of 2,900,000 people, 50.02% support the president, which is much more reliable because it's almost all the samples, so you know that who will win, people believe much more this. So the idea is that when they're making judgments, the majority of people, including us, I mean, by us we mean the people that are informed in these errors, we persist in assigning confidence by the mean and not by the variance, not by the reliability. Okay, so this is the classic idea. And another example, people like Luca Bonatti, who are here, give good. So of course, this is a problem, but it's also the virtue of human cognition. So imagine there are 10,000 balls in a bag, like an experiment typical of Luca. And I take one ball and it's red. And I take a second ball and it's red. And I take the third ball and it's red. And I take the fourth ball and it's red. I take the fifth ball. What color is it going to be? From your heart, really? It's going to be red. I mean, there's no way it's going to be, or you doubt that it's going to be red.
If you're told that there are different colors, you may expect that there will be another ball.
You don't know. You're not told anything. You're just told what I told you. The point is that you think, I mean, you really think that they're red, because the fact that people forget is that 4 samples out of 10,000 is almost nothing. Still, we make theories and rules out of very sparse data. This is actually what actually maybe the virtue of human cognition, but it's also a problem of actually that we are very confident of things for which we have actually very sparse data. So I want to give you the idea that, the majority, so the way that the people have solved the conundrum that I presented before is that you can say, well, economic decisions are just very hard. And since they're very hard, people do n'importe quoi in French, whatever. I mean, people do whatever they can. You know, they just do whatever is available for them. But in decisions which are low-dimensional decisions, then people wouldn't work like that. The point I want to make is that the way our brain is organized is actually a way that we tend to make this error because we make very bad estimations for the variance. So I'd like to take this idea to the domain, not of economic decisions, but of low-level decisions where we can actually do physiology. And again, I will not have the time to show you the physiology, but we do. So here's the idea. Imagine that you have 2 distributions, right? And you have to respond. Imagine that you have an internal distribution of, for instance, of how many votes a candidate is going to get. And you can estimate that from a sample that you have, and this sample that you have errors. And imagine that you have 2 different distributions. One that's very wide, because it's a very small poll, so you have a lot of errors. And one that's much more precise. The variance is much less. In this case, I've chosen the mean to be the same, just for simplicity. And the only thing that changes is the variance. Then you can compute the number of errors just by looking, if you were to run this many times, just by comparing how many counts you have in this side of the distribution and how many counts you have in this side of the distribution. And from very basic signal detection theory, you get what you should and what you expect and what happens, which is that as the variance gets lower, then the number of errors decreases. The probability of hitting the wrong side of the decision threshold just by noise actually decreases as the variance lowers. And so what you get is that performance decreases. Now imagine so this is for choice. And this is very well known, and there's nothing to learn there. Now the question is how this statement, I am sure that president will win if I am told, imagine that my criteria, I'm a political conseller, and I need to make an opinion, and I'll make my opinion that we will really win the election if the poll tells us that, that we get about 70% of the votes. This is what a typical political person will do. If we get that, then we're confident. Forgetting the fact that the majority of people should use, which is that I should know how many people are there in the poll. I will construct confidence just using the mean. Now, there's something which is pretty interesting there that you will get in this idea, and then the next 5 slides actually will just be an iteration of this idea. And it's a form of stochastic resonance. What you get here is that, so what I'm saying is, this is now my bar, so this is my bar for the decision. For the decision, if I am to the right, I will say we win. If I am to the left, I'll say we lose. And the first thing I showed you is that as it gets wider, the probability of getting in this side increases, so there are more errors. But something interesting happens also, that if you just think this as random samples, the probability of getting a high confidence sample is also greater. Because when I have a lot of variability, everything can happen, including that I can go for one sample to the very far right, and so I can get something that I'm very convinced. And so again, this is just something that's being inflated by noise. It's one of the many examples of a stochastic resonance, of a process in which you inject noise to the system and you get something that looks like signal just by random fluctuations of this noise. And so the point is that if this distribution would be very narrow, I would never pass the high confidence threshold, but if the distribution is very wide, then I would pass it many times. And then you get a very strange prediction. Very strange. So all this, I think, seems reasonable to the majority of you. It doesn't seem to be a lot of trick. But there is a very strong prediction, which is that as I increase the variance, I should get worse and worse and worse. So I should be lowering performance, but I should be boosting confidence. I should be more confident. So this is a typical error of confidence. I'm going to be more and more and more confident as I get worse and worse and worse. And this does not happen just because of a random magic or something, but because we do have a system of confidence that's not making a d prime out of this as it should, or it's computing entire variance, but it has a fixed threshold and ascribes something with high confidence whenever a random sample actually exceeds this value. And so I want to show you 2 pieces of evidence from this. One comes from the study of Ganev and in New York. So this is the last author, and this is Haquan Lau. I think this is a very beautiful and nice study, which was the inspiration for the one I'm going to tell you before. So what he did, so the idea here is to inject noise in the brain, again, in a very uncontrolled manner, using RTMS. So the idea is that you just pulse magnetic pulses, but it's not a phasic pulse, but rather you go boom, 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 boom during 10 minutes, and this screws the cortex on a way that's hopefully reversible, but that can be thought of, and I'm being weak of this because I think we don't have much more information, as injecting noise, or as changing the signal-to-noise ratio. And so what he does is, there's an occipital, so this is a visual task where you have to do, I think it was a luminance discrimination, I forgot, but it could be, it's a V1 task. It could be either contrast discrimination or maybe orientation, tilt, I don't remember exactly the task. It's published a few years ago, so you can look at that. And so what he does that is under 2 pulse condition. One is an occipital pulse, and the other one is just the control, so it's pulsing, but in a way that should not affect. And what you get here is performance in the task, and each one of these is one subject. So again, I like this because you see it's a weak effect, but it's very reliable. You get it in 1, 2, 3, 4, 5, 6 of 6 subjects, and then in the group you get a quite significant thing, is that when you pulse V1, you inject noise, and people get worse in how they perform. So again, this is not a lot of magic. You inject variance, and people do worse than they should. But then the question is what happens with confidence, and if someone give you a feeling for what should happen, and you see that actually confidence increases when you're pulsing in the occipital cortex. And so again, I'll repeat this because I think it's important. You see this seems extremely irrational. People are being more and more confident when they perform worse. We have a manipulation that does 2 things. It makes people do worse, but it makes them be more confident about what they're doing. And so there is an idea here, which is an underlying idea, which was worked in behavioral economics, and then now we're taking into standard models of decision making, which is what people are doing is they do have a threshold for, they do have internal distributions, but they do have a threshold which has a fixed value on the mean. So here's this was done by Ariel Silverberg last year in the lab, and it's the same idea I'd like to present. So, but but where we can control the noise in the system. We cannot control the internal noise. We also now have single-cell physiology, so we can control the noise at the neuronal representations. But here we can inject external noise and assume that the internal noise of representation of orientation will increase as we increase the jitter between all these things. So all of these have the same, they're all tilted to the right, and subjects have to respond whether on average all this field of oriented element is tilted to the right or to the left. We can change the mean average of these things, and as this is done, performance gets better, but we could also change the variance of these, and so this is from blue to red to green. Here it's red, green, and blue, and you see that as we increase the jitter, actually we get, as there's less jitter on green, there's better performance, and as the variance increases, people perform worse. And now, again, the two models, this is exactly the same idea I told you before. One is a formal signal detection model, or any decision model you'd like to make, in which people are making real probabilistic inferences, in which they take samples, they know something about the variability from which the sample is taken, and from there they compute confidence, and you get that confidence mimics performance. There is a change in the curvature of this, because the confidence is quadratic in a way, because it's a second readout. But essentially you see that the shape of these curves and the shape of these curves is essentially the same, and I think it's what's reasonable. As thing gets more variable, which is from up to down, then people decrease their performance, and correspondingly, an optimal decision maker also decrease their confidence. As you make the problem more difficult for me, I'm worse, and I feel that I'm doing worse. Now, if you have the model that I showed you before, in which you say, whenever I'm above a certain value, then what I expect is that as I make distributions wider, as I just did before, then you increase the likelihood of just hitting by chance this border, and again, this is this confidence fueled by noise, and you get the opposite effect, in which you get that the highest confidence is found for the most unreliable stimuli. And so this is just theory, and the question is how people behave. I'm going to skip this because it's repetition, and the answer is that people behave exactly as is predicted by a model with a fixed threshold. So again, the point here is that we can try to take so this is it, and something, this is technical, and it's late now and I could not explain it, but one more thing is that you get this from, let me give you now the last idea. Maybe that shouldn't go to the very end of the talk. But when you see this, actually, you get a feeling that the variance, obviously you get a feeling that the variance of this is higher than the variance of that. So it's not that people actually cannot estimate the variance, it's that they do not have a very good estimate of the variance. Now, as it happens, because the variance is actually dividing when you do a D prime, what happens is that just a little bit of error, you know when I don't know if you took courses on statistical theory or error propagation or whatever, but when you have a number that you estimate has a small value and you estimate it wrong, this is not very bad unless this number is dividing. Because dividing by 0, dividing by 0.1, or dividing by 0.2 is very, very different, because it amplifies the noise a lot. So what happens in confidence, and this is the solution of why we estimate the variance so badly, even when we perceive that we can do it, is that small perturbations in the variance, even a small change in the variance, doesn't need to be completely blind to the variance. Just small perturbations are actually enough to screw completely the formal estimation, and then people just rely. They do the best model they can, which is because the variance is very unstable, because it's dividing, then you actually have to use the only thing which you can, which is the mean, and so this gives the confidence influences by the mean. I'm not going to show you the data now, but I tell you, and with this I finish, that this same thing we have, so with Mike Shadlen and with Ariel, who was my grad student, who is now with Mike, doing his postdoc with Mike, we repeated this experiment with monkeys, and we do find that the exact same result that I've showed in psychophysics hold for the monkeys. So if you increase noise in the neuronal representation, in a motion, here it's in a motion detection task, the monkeys will do worse, but will feel more confident. And so again, the point that I'd like to make with this is that somehow what we could do is try to reconcile. To me, it's interesting when many times in science, and I'd like to finish with this general commentary, many times in science it happens to me. I go to it's a high dimensional problem, so you go to a talk and you listen to a story, it all feels reasonable, it's all based on reasonable data, and it has a conclusion. And then you go to another study, another talk, and it's all reasonable, it's all well done, it's based on solid data, but it reaches the opposite conclusion. And this happens particularly, I think, in neuroscience. This doesn't happen so much in physics, but it happens a lot in neuroscience, and especially in cognitive neuroscience. And I think that something which is interesting here in the field of confidence is to try to understand why these differences may happen, why a whole community may find. And in short, again, I think that the idea is that I'd like to finish saying that I think that our current model for this, and we have now a review paper that's coming out on this that probably summarizes this idea, is that the brain does a very good job in computing probability distributions because it's a parallel machine, because it's very good on computing, because it can do a number of things that can do that. But these distributions are often, and the majority of cases, not accessible to the confidence system, which then needs to do simple models, approximations of this, which is what people used to call heuristics, but they are just estimations of these readouts, which results in the somehow paradox that the brain is perfectly good in computing distributions, yet we are completely lousy, very bad, and have very stereotypical errors when we assign confidence. And this last thing, I think it's very important. I like to come back to the beginning, which is that these errors in confidence actually are a huge problem in society, are a huge problem when, again, in medical communication, are a huge problem when people get into communities. Bahadur Barami in UCL does these experiments in which you just get a group, 4 people. Like I was telling you before, you have your opinion, I have my opinion, and how we should weight this. When it gets to neurons of the occipital and the temporal cortex, they do a very good job. When it's about people, and that's something the majority of you know, there's a problem, because we tend to trust the person that is more confident. But what I just showed you before is that the person that's more confident needs not to be, and usually is not the person that knows more, is the person that has an idiosyncratic way of strongly expressing their opinion and their confidence. So this is something that I think as societies maybe we should change. So thank you very much. And thank you.
Thank you very much for a great presentation, and now I just have to find the microphone. Who stole the microphone? You did. Yeah. Why did you do that? Okay, pose your question. With confidence, please.
Thanks for the
Oh. What's going on, Sietse? My lovely assistant Sietse is...
Okay, thank you. In some motion perception experiments from Shadlin's lab, the monkeys, where the dot coherence can vary, the monkeys had a choice of indicating a direction or a third option, opting out.
Yeah.
And on the more difficult trials, they did opt out. That is when you would expect them to have less confidence, they made the choice that indicated less confidence when they should have.
Yeah.
So in what way is that consistent with your...
No, this is exactly consistent. So because, so in the one experiment, so the one experiment you are saying is, so I'll just maybe give a more comment for people that are not so familiar with this. As I said in the beginning, there are different ways of measuring confidence. One is just reporting them. The other one is by implicit ways. In animals, there are 2 traditional ways of doing that. One is that you can have a choice, and if you're correct, you'll get 5 drops of juice, and if you're wrong, you'll get 0 drops of juice. Or you can choose what's so-called opt-out, or like an I don't know option, where you just have a safe bet where you'll get 1 drop of juice. And so the idea is that this is a proxy for confidence. Another one that has been studied by a lot is waiting time. So if you have a reward, you may be willing to stay in the box to wait for this reward. And the amount of time that a rat or a mice is willing to wait for that depends on things that we think that are a proxy for confidence. So in the study of Mike, what they change is this variable here, so the decision signal. And we show that with decision signal, confidence increases. This is what's shown here. Mike didn't do the experiment of fixing the decision signal but changing the noise. Actually, we've done that now with him, and the response is exactly like humans. So there are 2 ways in which you can change confidence in these simple decisions. One of them is fixing the variance and increasing the signal. If you do that, you increase performance and you increase confidence, and also things happen with response time, which I didn't have time to show here. But the question is that this is not the only manipulation. So it's not that's the one thing you're referring to, and this is also shown here in the fact that these lines increase. I went for all, not for this variance level where it gets very noisy, but for all the other variance levels, And if I go farther here, as you do increase the signal, people get better, as in Mike's monkeys, but they're also more confident. This is the experiment you're referring to, and this is completely consistent with that. The experiment that had not been done, and it's now done, not published, but now the experiment has been done, and there are 2 monkeys, and it's quite consistent, is that as you do increase the variance, so you go in this dimension, monkeys do get worse, but they are more confident. So this is actually completely consistent with what's found in
So in variance, with increased variance, there are more outliers.
Yeah.
So do you think the brain has some intrinsic sensitivity to outliers as potentially carrying a lot of signal?
Yeah, so
That
that's exactly, yeah. So
we
this
overweight outliers.
So this is what I try to mark here. So one Kahneman idea is that when you make decisions with a lot of variance, you are fixed on some tokens. So it's just fixed on a cluster. And so the idea is that when my idea of what's going on here is that when you see this, you find a patch of this highly variable, and somehow you focus there. And we have an experiment where people actually draw after they do the experiment. What do they think that is the region that they made? They have, of course, to make it an entire patch. But we tell them that if for any reason they didn't do that, to try to give their estimate. And so when you compute the variance relative only to this region, so of course if you're only looking at this, and this popped out on you and you ignore the rest, you should be very confident because it's highly tilted to the right, and this is very low variance. So if you're not computing the variance entirely, but only just on a pop out or something that's salient within a texture, then you will get these results. And these models do work. We have this in the psychophysics. We do not have this yet in the physiology. But I think this is exactly what's happening, that the brain cannot concentrate in the entire distribution. So either it doesn't calculate it, or it calculates just tokens. This is a slightly different interpretation. In any case, this is open. I mean, this is something we're working on. And there are a bit of 2 different ideas, which are very similar, but not quite the same.
So I just wanted to try to understand. So the way the reason this is paradoxical, as I understood, is because people weren't able to estimate the variance correctly. They just see that there is a large variance, but they nevertheless estimate the mean. If the mean is large, they say, I'm confident.
Yeah.
Had they estimated the variance correctly, they would have said, well, I'm not so confident because there is a lot of noise here.
Yeah, well, not sure. Is that the question, or you want to?
So I'm just trying to see how you're doing it now with the random dot motion. Because so here you can estimate the variance. Now if I drop those lines one by one and I ask you respond as soon as you're confident, which I guess is the equivalent in the random dot motion, if you're doing the reaction time version of the task, which I guess that's what Shannon is doing. If I see 5 lines going to the right, I say, this is a right stimulus, and I'm very confident.
No, I see.
Then I didn't have enough information to estimate the variance.
So first I want to respond. I think your question is good in 2 things. First, that lets me clarify something, and then I'll go to the end of your question. First, I agree with what you say, but we do not have the data. So I think that people are actually bad in estimating the variance, but we did not ask them to estimate the variance and to report it. So there are 2 reasons why subjects may. So what we know, and this is the paradoxical thing, this is the thing we know for sure, is that we have a parametric manipulation that increases performance and decreases the confidence. This is weird. I mean, when you do better, you should be more confident, and we show that we can completely correlate these things. Now, our idea for that is that people do a bad job estimating the confidence. There is another possibility, which is that they can estimate the confidence well, but they don't use it. So they don't understand that they have to use the variance. This would be, so for instance, in the example of 70% poll of 300 people, there you have the reliability. It's in your eyes. You know the total amount, so it's easy. But there is a frame in which you don't even think about that. So it's 2 different things. My view is that people cannot estimate the variance well, which is related to what we were discussing before, but I don't know. I mean, we haven't shown that. To this, I could have another experiment which we haven't done, in which we ask them to manipulate the variance. Now, as for motion, I think that if I understand your question, I think that the issue is that in motion, the critical value is coherence. So somehow the decision signal and the variance are confounded because the amount of dots. Now, you can still do manipulation, but increasing the randomness of the random dots, which is something that wouldn't change the mean direction of motion, but actually would change the amount of random movement. Another thing that you could change is changing consistent in time. And another thing which is what we did is just look at random fluctuations and record in neurons and try to see what's the variability in neurons and relate that to, because as I said, I mean, of course, all these inferences are made from internal representations. And there's an assumption here, which seems very reasonable, but I don't know if it's true, which is that if I were to measure neurons in the primary visual cortex, and this we haven't done, in this case, and in this case, I would see that there's much more, and I were to do a normative computation of orientation, it's that there should be much more internal noise in this case than in this case here. I'm controlling external noise on a way that I hope that this external noise will drive internal. By internal, I mean noise in the variability in the neuronal population representing this quantity. So in motion, you can play different games, as I said, or you can just let it happen randomly and just try to relate the noise that you measure within neurons and then relate it to response time and to confidence. There's a whole thing I skipped, but this also comes to your question, which is response time. I mean, of course, these things are related, and when you have these random fluctuations, then So the idea is that if you have a fixed threshold and you hit the threshold, then of course this threshold by definition is your confidence. So in any diffusion model, in any drift diffusion model, you have, in the moment that you hit the threshold, you lose information about what was the noise or the signal of the system. The only place that you have this information, and this is the work that we've done here with Andrea and with Gustavo Deco, is in the time it takes you to make the decision. So in a diffusion process, you can hit the threshold very rapidly if you have a lot of signal, or you can just drift to infinite until you hit the threshold. So this is why also often an heuristics for confidence is the time it takes you to make a decision. If there's a decision and you think a lot about that, it's maybe because you're doubting, and maybe you can sense the workings of the diffusion that's going up and down, and eventually it will hit the threshold if you give it enough time. So this also relates to this idea, which I didn't have so much time to express. Yep.
Hi, thank you for the talk. It's been very interesting. I'd like to ask what you think about if there's maybe an evolutionary advantage to actually having this type of performance.
Yeah.
So, for example, you're in a high-risk scenario. You're being chased, and you come up with an action plan.
Yeah.
Which you don't know its outcome, but you have to be confident, because if you stop to think, you're dead.
Of course. Yeah. And this is very good question. And yeah, I like the. You said good talk, so I'll say good question. We're friends. But no, but I feel. I mean, it's a. This goes to the very difficult question, which is why we do have this bias. The majority of us have a bias for overconfidence, and I think you're hitting on the right response. For one, and this has been much more studied in the literature of optimism, which is where when you're over optimistic, you have an excess of confidence on something that's going to happen in the future. And the example I like the most is people marrying, right? I mean, if you ask two people, are you married? Okay, then probably you're a rational person. But if you ask two people in the moment they're getting married, what's the likelihood that you will end your marriage? People will say, I mean, 0. I mean, getting married, we love each other. Now, the probability is extremely high. It's a fact. I mean, unless you think that you're out of the rule. I mean, the majority of the people get divorced. I mean, it happens. Now you feel it can never happen and it's impossible. And so, but this brings your question too, because if you were to think that at that time, you probably wouldn't do it. So there are certain things. Now the people that work on optimism, it's very interesting, because this that looks like the same I could say, about having childs and about especially having the second, but and so on. But it does have a risk, right? So the typical example is driving. This has changed a bit now, but many people, when they drive with cell phones, right? The majority of people think when they're using a cell phone, they're very bad in estimating the probabilities that something will happen for doing that. Again, you're doing different things, which is concentrating on small samples. You do not think that you're within a distribution. You see yourself outside of a distribution and you're a token. The whole things we said here, and so people do it. And there you have an example where there's really no good reason for doing that. So I think that there's an evolutionary reason which you're bringing here, which is that and another way of saying it is that the opposite of optimism, which is pessimism, is very close to depression. So there is an idea which is that if you're, it's like in Star Wars, I forgot the R3, not R2D2, the other robot, C3PO, you know, he's a rationalist, and so he's going on the meteorites, and he says, we have a 0.001 probability of surviving, and Han Solo says, you know, shut up, I mean, because it's the only thing I can do, and I don't want to think about probabilities now, I need to go. So, I mean, I think that you're bringing an interesting question, very, very profound question, which has exceptions, where I think that as a society, recognizing that we have these distortions, again, in medical care, in driving, in certain situations where they're nocive, where they do not help, I think that we'd do a better job if we recognize that and try to change it, which is extremely hard, because as I said, it's very stereotypical, but it can be changed.
Okay, thank you for your talking. I want to clarify something, because maybe I didn't understand. You're talking about stochastic resonance.
Yeah.
Okay, so I want to be sure what is the weak signal that you want to maximize using the noise. You know, what's noise in your model, what's the signal you're maximizing?
Yeah, okay.
Because that's the normal procedure.
I'd say like in language. I think it's a weak and illicit metaphor, so I apologize. What I meant was the idea that so the weak signal here, but I'll give you, so it's not really stochastic resonance. I just wanted to frame the idea that you get somewhere by noise, but I'll give you the weak signal here if I find that, and the just to give you the flavor of it. But assuming an understanding that I don't want to make this strong point that this is stochastic resonance. We've not done this model, but just as a weak idea that you get somewhere by noise. So here your weak signal. So here you have to respond right or left, and your weak signal is this value. You're measuring something that you're not going to be high confident. Because it's very low. Of course, if you're average, if your mean signal will be of 90%, you're going to be confident. So this is the weak signal. Now, if the jittering that you have by noise is not too large, then you do not get past this barrier. If you get sufficient noise and you have a low value of difference, but you can eventually be pushed up by noise, then you go and get on the other side of the threshold. What we certainly do not have here is a resonance in this sense, although you might, because if you combine this with the halo effect and you make your claim, so you go there, so you're going to bet right, and then you're going to keep and you're going to circle this, I wouldn't be surprised, although, again, we've not done that, if you could find something in which small perturbations may take you on the other side. This makes yourself have a commitment that this is going to be right, and then you stick onto this and eventually get a resonance and an amplification of this noise. But weak metaphor. Sorry?
Your noise has to be biased to make that work.
Yeah.
If you would take this just from your standard normal distribution noise.
It wouldn't, because it can take you to the other side. But the second response to him, and I think that this happens actually in the first part of the talk I couldn't, is that once you've so this is usually here, this is static, but of course this is sampled in time. So the internal distribution, your posterior is all the time changing. And once you've made a call, and this call is maybe biased by resonance, by noise, then your distribution may be skewed and maybe asymmetric and maybe shifted to another side just because you made this call. This is actually what happens with confirmation bias. So again, very weak metaphor just as an idea of framing something, but I think that it's something which may be drifted by noise, and there may be some asymmetry that may be the resonance.
Maria, go for it.
Okay. Hi. Do you think, well, nice talk, but do you think that confidence, yeah.
Good question too.
I'm motivated.
Very good question.
Do you think that confidence can be trained in that sense?
Yeah.
And how do you think that this could affect a learning process?
Yeah, so Kahneman says no. I say yes. So, and again, you can, again, reliability, he's a Nobel Prize, and but again, the question is why two different questions may both be true. He's right in that people are extremely stubborn in the way they think about confidence. And for instance, this is, again, the essence of optimism. And like people like Tali Sharot and so on, they've studied that a lot. There's the idea that once, and this happens in many domains, confidence also in social confidence, in trust. There's people you trust, people you don't trust, like like Woody Allen, you may trust him. And he does a bad film, and you will still trust him. And he does a bad film, and you will still trust him. And he has to do many bad films for you to change his opinion. And so the idea is that the entire idea of updating this probability distribution, which works very well in some domains, in many of real life decisions, it doesn't work. People are extremely stubborn, even in face of the evidence that they should work in other ways. So there are two ideas here. One is the Giger-Insert idea, which many of you may be familiar, which is a response to Kahneman, which is that people are very bad working with probabilities because probabilities are expressed in the wrong format. And he's done that I think with quite a lot of success in working with medical students, where he shows that people, when you start thinking about conditional probabilities, people screw. Like, even if they're good mathematicians, and he shows that as they higher into medical school, they make worse and worse because they're using the wrong heuristics. But if instead of in this language, you express probabilities in frequencies, like you do the entire tree, and you say, well, if you've got that and that and that, then of 1,000 people, 733 are in this condition, 125. So do not thinking in a language of probabilities, then people respond much better. So it may be the case. This is Giger-Insert versus Kahneman, long story, that if we were to rephrase probabilities on a language that's more natural for us, we could compute variance better, and if we do compute variance better, then we could compute. Then the other thing is, so we do, and other people are doing experiments to calibrate probabilities, and on that people do get well. So you can learn that you are on one side or on the other side of the bar, and this actually transfers to other domains. So short answer is it's a difficult thing to train. It's not like you understand the concept, and once you have to understand the concept, the next day you go out and you calculate probabilities well. It takes a lot of effort. These two efforts, in my view, maybe on specific trainings, like there's trainings for, change other biases. Like, for instance, in the US, some judges goes to training to avoid empathy, because when you're more, judges, which is very related to the halo effect, when there's a person that looks like you or is nice or something, you treat them differently than a person that doesn't look like you or is not nice. And this is a very strong bias that's carved within all of us, but that can be reversed if you're aware of that with a lot of training and with a lot of executive control. You have to be sitting in the situation and saying, I am like that, I have to avoid this, seeing it from far away, and so on. So these things can be changed, but they're very difficult, I think.
Okay, go ahead.
I would say you talk when it was a great talk. Don't say it was a question. It is a good question.
That's a great introduction.
I forgot the question.
Exactly.
You said in another experiment you have subject to mark the region of, of the patch where they were mostly looking at, right? Have you seen effect of the size of this?
No, this is an experiment we're doing now, like really now. So I cannot. I mean, the hope, it comes from the question we discussed before, on the hope that we could get the idea that people are concentrating on subsamples of the stimuli, but I cannot say anything. Not because I don't want to, but just because I think it would be very lousy. We are just like seeing the data now. So yes.
So lovely talk. Really enjoyed it. So you've talked a lot about why human decision making is non-optimal.
Yeah.
But you also said that there's another whole domain of sensory cue integration and all that kind of stuff where things are optimal.
Yeah.
So do you think that this is just different brain circuits with different rules, or like how do you reconcile those two literatures?
Yeah, okay, so one thing we're trying to do is to replicate the Wolpert experiment of Q integration, where we ask subjects to report both variances and then see if you can make a judgment based on the distribution that they assign for each modality, if you would get the response that they themselves are making this computation. When Wolpert models this, he assumes that you have an internal representation in one modality, an internal representation in another modality, and you weight them through in an optimal manner, and subjects do that. Then we were saying that when they have to speak out their confidence, they cannot do it. So one thing which I think would be interesting, and I think no one has done, maybe it's been, but I'm not aware of, would be taking this example, which is the horse battle of optimal integration of distributions, or any other one of these, and try to get subjects report all the estimates that we can of their distributions and see how this fails exactly. Alex Pouget, his idea is that, his idea with this is that this is nothing specific of confidence, but of human cognition. And he may be right. So what he says is that so take the motion task. I mean, like to give them one of the most studied. I mean, anyone that has done this task knows that if you get one subject and you ask them to do the task, you just throw away the data. That you need to get subjects actually to get trained on this, because you need to get a mapping between a sensory quantity and this mapping does not happen immediately, but you need to be able to read out sensory information so that it can be expressed on a motor effector or on a very simple choice task. And so Alex's claim is that you have these neurons that encode distribution probabilities, and it is a learning process, as with any other cognitive task, just to be able to map these quantities on reasonable readout functions that will express them for whatever a task requires. So in multisensory integration, this may be an overtrained task. We are used to that. It's a task that we've done a lot, or maybe even these subjects have been substantially trained or something, that we've learned to make the mapping of these quantities to the effector that is required. When this is, we may have some flexibility of that compared to monkeys and to other, but maybe this flexibility is not complete in the sense that those quantities are not there available and to be broadcasted to any effector or to any representation. So Alex and his view is that it's just an issue of learning, like in any other sensory motor task. That you have quantities. These quantities are there, represented in an implicit population. We do not decode. We do not know the exact code, and we need to learn this code with feedback, and this should be something that should be learned. So this may be a bit of. I'm not sure if I'm responding to your question, but I'm trying to say that yes, it depends on task settings. That you may have, that it may, so this is not very different from blind sight or from classic psychophysics. I mean, it's known, I mean, the fact that there's information somewhere in the brain that can be used in certain task settings for certain motor effectors, for certain responses, doesn't mean that we have complete flexibility for actually accessing this from the language system or for a confidence report and maybe this precise mapping needs to be learned. And another possibility, so this would be Alex's view, another possibility is that this needs to be learned, but also it conflicts with a bias of that we also have a certain way of reading probability distributions, which is, so this comes on the very first part of my talk of whether the readout of probability, there's a general system for that. So Sigman thinks that the orbitofrontal cortex is somehow dedicated for an abstract system of confidence. People like Dolan or Fried or Fleming think that Rodman area 10 or the right frontal cortex actually plays a role on that. And if this were the case, it may be that it's not just learning a particular readout, but also maybe unlearning a specific way that the confidence system has of actually accessing information about wide distributions in other regions of the cortex. I'm not sure if was the question or?
So you're saying that the neurons are optimal, that the neurons are optimal, but frontal readout of those neurons is non-optimal.
This is the solution, I think. And that other readouts may be. So that there may be configured systems. So what I'm saying is it's not because it's too complex to read out this information. It's because building the stereotypical circuits that read this information from the frontal cortex so it's available for conscious report or for language or for whatever is something that either takes a lot of training or conflicts with the way that the frontal cortex reads information from the ventral cortex. I think, so when I show so this may not be, I'm thinking, so the way I think that is in ventral or temporal or occipital to more frontal, but even in the frontal cortex it may be the case, like in the Dolan paper, that the medial to lateral frontal cortex, there may be an issue of how that a good encoding of probabilities that needs to be read for report, and that this may be wired in different ways in different people. I think this is the solution, yeah. Go for it.
Hi. I'm not sure to understand the last slides. What I would like to understand is if your last results, yes. I'm used to think to the confidence as increasing with the correct number of performance or something like this, and to decrease with the errors, increasing the, I don't know, the difficulty of the task or whatever.
Yeah.
It seems to me, but maybe I'm not understanding your results, that with these results, it's something in another way around?
Yeah, it's a bit different. It's somehow, so here I'm showing confidence. I'm not separating this by errors or by correct responses. I think you can get something very different from that. So the result, again, simply is that you increase the variance of something. On doing that, you get the classical result on choice. Performance decreases, but you get a paradoxical effect on confidence, which is that confidence is boosted. And is boosted both on correct trials and is also boosted on error trials. And the reason that you're doing that is that you're just widening the distribution. And so if you have a cutoff of confidence, which you're saying, I'm confident whenever I get a sample which is beyond a certain value, ignoring the fact that this sample gets from a very wide distribution, then I am high confident. So you increase the confidence, both of the correct errors. You also get high confidence in correct trials, which you can get when the variance is lower. I think it's not. I think it's not. Maybe we need to work. I'm not so sure. That's what I think it's not. I cannot. Maybe we can talk this a little bit later because I'm not exactly sure about how this relates to what you are saying. But I think it doesn't. I'm not sure.
So I've got 2 comments. I'm not sure I've really worked it out in my head, but I'll try and say what I'm thinking. So we have multiple systems in the brain, which when you ask a question, such as the one you pose, can all contribute. So Antonio Damasio would say in some of these decision-making systems that we have readouts of our sort of bodily understanding of things, which may be these more subconscious mechanisms that you're talking about. He particularly talks about the somatic system as giving us a kind of gut feeling about things. But then you have patients like Phineas Gage where that's lost, and they still have a deliberative system, so they can deliberate about stuff and come up with an answer. So the fact that people don't behave as good statisticians I don't think it's that surprising, because they have multiple ways of thinking about a problem. If you give them a very abstract problem relative to their daily lives, like the outcome of an election in a country they know nothing about, then they may be able to hazard some guess. But generally, when you ask somebody a question, they will bring other systems to bear on that question. And the models that you're presenting are based on an assumption of sort of normal distributions. So you're saying, if you don't, and a statistician would say, if you don't know anything better, assume a normal distribution. But as humans, we operate all the time with all sorts of priors, and a lot of life isn't normally distributed. So when I come to one of your questions, why would I assume a normal distribution? Why wouldn't I assume multimodal distribution? In which case, if I see something over 70%, if I have some reason to believe that the underlying distribution isn't normal, then I might say that's good evidence for me. So I think I don't know if I buy this conclusion that humans are bad reasoners. I think we are good at reasoning from lots of different angles to a solution. We're not good at what machines do very well, which is working out the pure stats about a situation, particularly where you have low information.
Yeah, so honestly, I don't see very strong difference between what I said and what you just said. But you bring things and I'll try to explain why. On the last statement on whether humans are bad statisticians or not, I mean, of course, it depends on what you call bad or good. But the fact is that it's an empirical fact, and it doesn't depend on the models or in the reasons or in the mechanics on why this happens. It's a fact that humans tend to be very confident on situations where they shouldn't. Now, you may make the claim that the reason for that is because we don't have enough resources for that, so we are doing the best with the information we have. We do have certain experiments where we show that this is not the case, because we do provide the variance, and subjects can use the variance for some of the things they are doing, yet they do not use it to make explicit reports of confidence. Now, on the Damasio thing, I think, so I skipped a whole part where, and again, this is something that we've been doing, and Mike Sheldon also, is I went fast on your question on the diffusion model to response time. And so, again, here you get the idea that you hit the threshold, and when you hit the threshold, this is your level of certainty in a diffusion process. If it's a race, it's a bit different. But people use, so I place the idea that time may be an heuristic for thinking about confidence. So one thing I could use, and people do that. They do that on so if you do if I'm doing an experiment, and you're looking at me, and you try to say how confident I am, and let's say the only thing you're not looking at the mirror, so you cannot say anything, you do pretty well, and you do pretty well just by looking at the vigor of my response. So how, if I respond like this, or if I respond like that, I made an exaggeration. People don't do that. The time of the response, and of course this for the majority of it is implicit, is unconscious. So this, I think that often the confidence system, because it cannot access information of certain distributions, either because it's unavailable or because it's encapsulated in a sense that it cannot be retrieved, it has to rely on the best model it can construct. And if I cannot access about information about the variance of distribution, then I need to have an heuristic, or again, what Puget would say, it's just an approximated model, which is the best model I can construct with the access I have to the data. And it may be that the best model that you may use at a certain point is not looking at neurons in MT, but is looking at your hands. Because your hands may have access, neurons in MT may go to LIP, and this may go somewhere that there's something in your hand that reveals the variability in MT better than looking at MT directly. So I completely agree with that. And actually we are trying to train subjects to use that. It could be, I do trust Damasio's idea, maybe not completely, but the idea that a lot of operations of the brain are more tangible to introspection, not by accessing them directly, because we cannot access all the regions of our brain, but by manifestations of it that are probably expressed in our body. So I do agree with what you said, and I see essentially no conflict except maybe the fact that I think we are a bad statistician, but that doesn't have anything to do with the model, but with an empirical fact. And again, it depends on what you call bad, but I think that we have many cases in which people do have the evidence, yet do not use it to make explicit confidence reports. But yeah.
No, were you finishing?
No, it's okay. Yeah, no,
okay.
Fine.
So thank you for the great talk. What do you think is the relationship between confident choices and habitual behavior?
And
habitual behavior? Yes. It's like the way you describe the problem is that the type of choices that always go through like an evaluation process. But then most of the choices that we do in our daily life now are completely habitual.
Yeah.
But I guess that those choices have gone through an evaluation process before.
Yeah.
So you don't have to evaluate it anymore.
Yeah.
So do you think that habitual behavior somehow requires the same circuits that you would see in value-based choices, or that's like somehow a type of knowledge is exported somewhere else?
Yeah.
To then be used automatically?
Look, short answer is I don't know. I really don't know. But I will try to. This said, I will try to tell you the one thing that pops to my mind, because it was just a recent an availability. A few days ago, in a meeting of confidence, we were with Rui Costa, who does a lot of work on here in Portugal, in the Champalimau, who does a lot of work on things that I think as habituation problems, and he presented this idea, which I think it's very well known, but I didn't know it, and I think it's a very famous thing, which is that in these reinforcement learning tasks, you have many dimensions, and these dimensions do have variance, and you don't know exactly what the task is because it's implicit. And what you get is through learning, a narrowing of the variance in the dimensions that are relevant for the problem. So I like this idea that you have like a big sphere of variance, and learning has to do with concentrating so it's a bit like doing PCA. It has to do with concentrating on what are the right dimensions in which the variance is informative for the task. So these together with things that have appeared here, I think that I've said about uncertainty, but uncertainty is a very vague concept. There's uncertainty in many dimensions, some of which are relevant for the task, and some of which are not. And this needs to, so for a good confident judgment, you need to calculate uncertainty, but you need to calculate over a dimension which is pertinent for the task. So one thing that I think that may happen, and maybe a problem, is that when we habituate to certain things, we do project the data to certain dimensions, and then we look at the, so when I was telling you before that maybe some things need to be unlearned, they may have to do, and this is completely speculative, I mean, I'm speaking on completely beyond the data and with not just an idea, but I think it may have to do with the idea that we have certain schemes of thought or schemes of decoding information which essentially correspond to projecting certain directions of the variance and looking at the variance there. So it may be that reading the variance well does not only have to do with integrating, doing wide integrals over a lot of neurons, but actually knowing the curves along which these integrals need to be done. And we may have, through habituations, certain ways of doing that, certain predispositions on doing that, and this may be part of what needs to be unlearned, which I think makes the problem difficult. Because I think, obviously, we have the way we read confidence has a lot of things which we do not reflect on them, but are very stereotypical. So again, it would be, I think, in the domain of habituation and things that we need to correct somehow. I don't know if this relates. It's the only thing that I thought that could relate to your question.
So to finish up, also, if you look at this slide, and given that you work with Mike Shetland, who's the champion of the drift diffusion model applied to decision making in the brain, we have actually shown, I mean, the drift diffusion model is interesting also because people believed it was well reflecting the actual rate that you can pull out of frontal areas in the brain that are involved in decision making. What we have shown, however, and I talked about this 2 days ago, if you manipulate the confidence of the animal, the confidence by imposing, for instance, an error history, and you look now at the confidence, how this relates to the response rate of neurons in decision-making areas, drift diffusion is out of the window. It's not explaining anymore or predicting performance in any way, right? So to what extent is now the way you are mixing a confidence variable with your decision variable really dependent on this drift diffusion model, or to what extent are you actually considering alternative dynamics of the decision-making process?
It's a very complicated question to be the last one, but it's a long one, especially. I'll try to respond this on reasonable time. First, I'll say that I agree. I think that diffusion model does have a problem, which is that the bound fix a given level of certainty. So it cannot work simply. I think that there's no way. So I mean, this is Wald and Turing. I mean, you fix what you think is a certain level of, and you wait enough time, whatever enough is enough, until you get this level of certainty. So if the diffusion model would be completely true, then people in this type of tasks will always respond with fixed confidence, which doesn't happen. So either you have to accept that there's a more sophisticated version of a diffusion model where you start lowering the threshold with time and playing tricky games on, or you have to understand that it's not a sufficient statistics. And so other alternative would be the race model, and there's a very famous idea, which you certainly know, on how to compute from this model's confidence, which is the Vickers balance, which is the idea that now you have two independent races, and in the very end of the race, you look at the difference between, now in certain data, this is not universal, but in a substantial amount of data, we showed also that this cannot be the case, that with the Vickers, that the balance of evidence, so this is what this actually, that I didn't show the data for that, but we demonstrate, essentially, this is the confirmation bias, and it has to do with the fact that people do not look at with the same weight the evidence in favor and against the choice they're making. So in a race, you have evidence in favor, evidence against, and then you just subtract the two evidence, but people do not give the same weight to these two things, so this cannot work. Mike now is going, and it's the same direction we are going, on one idea, which is that time may be a sufficient statistics for that. So that if you and of course and so this is what we've done in a formal model here with Gustavo and with Andrea, is that of course in a diffusion process, if it is a diffusion process, then time is related to the variance because the time it takes you to diffuse to the boundary just by pure diffusion relates these two coefficients. And so this is an idea that we are trying to, that in these dynamic processes, time plays an important role. And so then there is the issue of how you compute time, I mean, how neurons compute time. And it's interesting that there you can use the reverse idea, which is what we did here. So if you assume that you have integrators, and these integrators are not completely correlated, they're partially correlated, which is an idea that I think that many people working in the, like Mike doesn't like very much to say, and other people don't, but formally it works very well, at least. I don't know if empirically it's true or not, which is that you have sufficient independent integrators, and then you don't look at the average of them, but you look at the dispersion of them. This dispersion, because of the same reason, conveys time. So the idea is that with a population code that simply at the moment of the decision, the population code that simply at the moment of the decision computes the variance across all the integrators, and you use that as a proxy for confidence, this works extremely well and explains a lot of weird things that confidence is doing. So we think that this may be a reasonable possibility. It's just, but it needs empiric confirmation. But theoretically, it seems like a reasonable possibility.
Great. Well, Mariano, thank you very much. Also for your